Good evening, everyone. Welcome to the week number 6 related to structural analysis course. So, every week, this class is conducted to solve the problems related to topics what you have covered in the current week. This helps you in understanding the concepts based upon the numerical formulations or numerical solutions problems that we are trying to solve in this current session. Let me share my screen first, then we will go through the questions as well as the problems. So this is your week number this is your week number 6 related to structural analysis course. So my name is Pranav Mahajan. I am a PMRF scholar in structural engineering division from IIT Madras. So till now we have covered week 5. So up to week 5, what we have covered? We started with analysis of beams, and we have seen how we can draw shear force as well as the bending moment diagrams under different loading conditions. Then we have seen how we can determine degree of static indeterminacy, degree of kinematic indeterminacy, and based upon that we have classified the structures into statically determinate structures as well as statically indeterminate structures. So up to week 5 you have covered all the topics as well as the concepts that are required to analyze the frames, beams, and trusses which are statically determinate. So we started with trusses, in which we have solved the problems for trusses using method of joints as well as method of sections. Later on, to determine the deflections in the trusses, we have utilized unit load method, which is also known as principle of virtual work. And from that we are able to determine horizontal as well as the vertical deformation at different joints of the truss members. Later on, we move to beams and frames, which are statically determinate, in which we have seen the problems related to determining of slope and deflection using moment area method as well as conjugate beam method, and some problems related to unit load method and direct integration method. Okay, so today what we are covering is related to moving loads, because in actual scenario load cannot be in the static position. If you see any bridge, road, which is there in the in the structures, you can see the vehicle loads which are considered to be a live load. They are always moving. So to determine the influence of the moving load over the structure, we use influence line diagram. So what is an influence line diagram? So influence line diagram is a principle which we use to determine the reactions, shear force, as well as the bending moment at different points of the beams, utilizing the moving loads that are happening over the sections. So for this, we have one principle called as Muller Breslau Principle. So what is Muller Breslau Principle? So I think you have covered all of this in the week number 6, but still I will try to give you a brief description about that. So Muller Breslau Principle tells you that the influence line for any force response function in a structure is given by the deflected shape of the structure resulting from unit displacement or rotation corresponding to force and the moment under consideration. So what you generally do, if you are required to calculate shear force at any particular point, or you can say displacement at any particular point, you apply, or sorry, I will give you a reverse sense. If you are required to calculate the force in that particular joint, or you can suppose we can say at joint A we are expected to calculate the reaction at support A. So what we will do, we will give a unit displacement to that particular support, and due to that particular means due to that unit displacement, how the beam is changing the shape, that will give you the influence line diagram for that particular beam. Okay, so this is the general principle related to Muller Breslau principle. So it is based upon reciprocal theorem, or you can say Betty's theorem. What is the significance of this principle? It is used to find the effect of moving loads on a structure. Second, it will help you in finding out the live load location to get the maximum value of stress function. Based upon that only, you will be able to design your beams based upon the available materials. Because if you know the maximum stress is occurring on this member, then only you can decide what kind of material characteristic properties you are expected to take in the designing of the beam section. Third is to find out any stress function under critical loading condition. So same thing, that if you are expected to calculate under critical conditions, when suppose whole beam is covered with load, or half of the beam is covered with load, so which condition is more critical? Either full beam covered with the load, or up to a certain length, if the beam is covered, that is more critical. So that is also helps you in understanding using this Muller Breslau principle. Another benefit of using this Muller Breslau principle is it is applicable to both determinate as well as indeterminate structures. So it does not differentiate that whether the structure is determinate or indeterminate. Whatever kind of structure is this, based upon the type of moving load that is authoring over the structure, we will be able to determine the reactions, shear force, and bending moment at different sections of that beam section due to the moving loads. So, giving you a little bit description how this Muller Breslau principle works. So, suppose you have one portal frame, it is subjected to two concentrated loads P1 and P2. So due to this P1 and P2, if you see, the deflected shape of the beam or portal frame is given to you by these red lines. Another thing, if you take another system, like system 2, we are telling in this case, and instead of providing P1 and P2, now you are providing Q1 at the center of the P1 and P2, and then also you are getting one deflected profile. Now what Betti theorem says, we will write. So using Betti theorem, so Betti theorem tells you that force in system 1 when multiplied by displacement in system 2 will be equal to force in system 2 multiplied by displacement in system 1. So in this case, you can see you have two systems available. Now you can see that due to P1, what kind of displacement is authoring in system 2. So I have marked using red pointer. You can see there it is delta QP1. Similarly, using P2, you can see that in system 2, the displacement authoring is delta QP2. Now, if we take system 2, so in system 2, you can see that force authoring is Q1. Now, due to this force Q1, what kind of displacement is authoring at that point in system 1 is delta PQ1. So, if you know all the unknowns, you will be able to determine the value of deflections at different points. So, this is what the main principle behind Betti's theorem. Now, talking about how you will be able to determine the deflection profile. So suppose you have a continuous beam in which a point load is occurring between support A and B. So now due to this point load of 1 unit, you can see the displacement profile, how it looks like in system 1. So I will say this is your system 1. Okay. Now, as per Muller Breslau principle, if you are expected to calculate the reaction at point A, what you will do? You will provide the displacement at point A. So let's say we are providing the displacement delta A at point A. So due to that displacement delta A, correspondingly we will observe delta X to be the displacement below the load of 1 kilonewton. So now if we apply Betty's theorem in this case, what will happen? So applying Betty's theorem, again we can see that summation of forces in system 1 multiplied by displacement in system 2 will be equal to summation of forces in system 2 multiplied by displacement in system 1. Now what are the forces that are there in system 1? If I am trying to write, it would be, since Ay is in upward direction, I am taking it to be positive. So Ay into displacement in system 2 is delta A. Now second is 1 kilonewton, which is authoring is down in downward direction. So I am taking it to be negative. So 1 into delta X. Since at all other points it is 0, so I am not considering them. Now we will take system 2. So at system 2, you can see that Fa is the reaction force, and due to that, displacement at system 1 is 0. Okay, so solving this, what you will get, that reaction force Ay will be equal to delta X upon delta A. That means it is some weighted function of delta A. Okay, so if I consider, or if I scale the delta A to be 1, so if delta A is scaled to 1, what you will get? So then you will get Ay to be equal to delta X. Fine? That means if I am trying to signify what I am getting, so your influence line diagram of reaction Ay is the deflected profile of the beam corresponding to delta X equal to 1 at joint A. Fine. So that means due to the application of unit displacement at point A, you will observe the deflection profile of the beam, and if you apply then the Betty's theorem, you will be able to get reactions at different points of the beam. Fine. So now let's solve some problems related to influence line diagram. So first question is, which method is used to draw the influence line diagram of an indeterminate structure? So I already told you that Muller Breslau principle is applicable to both determinate as well as indeterminate structures. So which method is? It would be Muller Breslau principle. Okay. Second question is, for what type of structures Muller Breslau principle is applicable? So as we have already seen in the definition, that Muller Breslau principle is applicable for both determinate as well as indeterminate structures. Fine. So this is the basic law, or you can say theorem, that is applicable in solving the problems related to influence line diagram. So let's solve few problems related to this. So your first question is, draw the influence line diagram shape for the shear force at point C for the following beam. So if you have to determine the shear force of the shear force at point C, what you will do? You will take a unit load and you will keep at two different points, because this beam we can split into two cases when the load is kept between A and C. So I will copy this, then it will be easy for you to understand. So let's solve this problem. So let's say I am keeping the load first between A and C. So if this is my location of keeping the load, and it is, let's say it is at a distance of x. Okay, so case 1, unit load kept between A and C. So in this case, you will observe some reactions also. So let's say I am marking the reactions to be RA and this to be RB. So what you will observe? You will observe that shear force at C. So first, how you will determine the reactions? You directly apply this. So if this is h, that means other length will be 9 minus h. Okay, so your RA, how you will define it? You will find it to be 1 minus h upon a 9. Okay, if you want me to solve this, I can tell you how it came. Suppose you are taking moment about a to be equal to 0, you will get RB into 9 to be equal to 1 into 3. This will give you RB to be equal to 3 upon 9. That is 1 by 3. Okay, so your RA will become 1 minus 1 by 3. Fine. So this is how you will calculate. But in this case, you can see or since I already taken it to be 1 into 3, but it would be h. Fine. So if it is h, not I am not taking it to be 3, then what you will get? So 1 into h, that will give you RB to be equal to h upon 9. So from this you will get RA to be equal to 1 minus h by 9. Fine. Similarly, you will get RB to be equal to h upon 9 because total is 1. Okay. So in this case, when h is equal to 0, that means load is at point A, that is at point A, your shear force at A will be equal to 0, because 1 minus 1 will become equal to 0. How it will come? Let me write it. It will be 1 minus 1. So your shear force at A will come out to be 0, because how what will happen? Your reaction force, and because your reaction force and the applied force are making it to be equal to 1. Fine. How it will come? Let me tell you. When in this case your RA will become equal to 1, therefore your shear force at H is equal to your shear force at C at A, sorry, it will become equal to 0, because uh, your applied load and your reaction force are coming to be same. So that's why your shear force at A will be equal to 0. So let's take another point. So when your H is equal to 3, so in that case, that means at point C, what will become? Your reaction force at A will become 1 minus 3 by 9. That means equal to 6 by 9 or 2 by 3. Fine. Therefore, your shear force at C will become 2 by 3, that is your reaction force, minus 1, which is your applied force, and it will become minus 1 by 3. Fine. Now take this beam again and see if your load is kept between B and C. So now if your load is kept between B and C and it is at a distance of H from A again. So in this case, again, what are the reactions you will be observing? So in this case also, if I am trying to find out the reactions, let me say this is reaction A, this is reaction B. So case 2, unit load kept between C and B. Fine. Now if unit load is kept between C and B, what will be the reactions? It will be same as earlier. RA will be equal to 1 minus H by 9. RB equal to H upon 9. Now when H is equal to 3, that is point C, because we are taking H to be from point A. Okay, that is point C. So again, if you see in this case, what will be the reaction? So RA will become 1 minus 3 by 9 equal to 2 by 3. Okay. And since load is between C and B, Therefore, your shear force at C will be equal to reaction force at A to be equal to 2 by 3. Fine. Now let's move to determine when it is at x is equal to 9. That means at support B. When x is equal to 9, that means point B. In this case, what will happen? Your reaction force RA will become 1 minus 9 minus 9 to be equal to 0. Okay. So, therefore, your shear force at C will become equal to 0. Or sorry, B will become equal to 0. So if we try to draw the ILD for this case, how it will look like? So let's say this is my total length of the beam and this is the point C. So from A to C, it is negative and then it is positive and then it is again become 0. So suppose this is your point A, this is your point C, this is your point B. As we have already calculated, between point A to point C, it is coming out to be minus 1 by 3. And after that, it is becoming to be 2 by 3. And then after that, it is becoming to be 0. So this is your ILD for shear force at C. So in easier term, if you are required to calculate shear force at C, you have the easiest formula, or you can, if you want to journalize this case, what you will do, you can say that the shear force at point where shear force at a point along the length of the beam can be seen to be equal to h upon L and 1 minus h upon L. Fine. I think this thing you have already seen in the class. Now I am not will give you detailed explanation for this. So let's move to another question. So your next question tells you if a uniformly distributed load of 30 kilonewton per meter with span of 2 meter is moving from left to right, that is of the beam AB as shown in the question 3, like we already seen. So what will be the absolute bending moment at point C? Okay, so that means a moving load is there of load intensity of 30 kilonewton per meter having length of 2 meters. So if it moves from right left to right in the beam, so now due to this you are expected to calculate what will be the maximum bending moment that we will observe in the beam. So let's say due to this beam, if there is point load over the beam, how the bending moment diagram will look like. So if we try to draw the bending moment profile for the beam, it will look like this. So due to concentrated load at point A, let me draw one more line here. So due to concentrated load of 1 kilonewton at point A, your deflection profile, oh sorry, your bending moment diagram will look like this. Okay, so to get, so you can see the slopes of this side and this side are totally different. Now you are expected to calculate the maximum value of bending moment. So that means your load should be distributed in what sense that you will get the maximum bending moment in the beam. So this is your ILD for bending moment at C. So to get, let me write with the black pen, it is good for you. So to get maximum bending moment at C, load will be placed at C in such a manner, in such a ratio, or I will write in such a ratio that your point C will divide the beam and the load in same ratio. Okay, now it's understood. That means you are expected to divide the load based upon the ratios distributed of the beam. So from left to right, the ratio is 3 by 9. So that means your load distribution will be, so your total length of the beam is 2 meter. So load distribution left side, I am writing it to be total length is 2 meter of the load into distribution. So what is the distribution? It is 3 by 9, that is 2 by 3 equal to 0.67. And this load distribution on the right side, how it will look like? It will be equal to 2 is the total length divided by 6 by 9. That means 4 upon 3, it will be equal to 1.33. Okay, now I will copy this diagram, then it will be easy for you to understand this thing. Fine. Now you are expected to divide the load in such a manner that you will observe the 0.67 to be here. That means this length should be 0.67 and this length should be 1.33. I will mark it here that this length should be 0.67 and this length should be 1.33. In this region only the load should be distributed. So now first, due to the unit load, what will be the maximum value of bending moment that we will observe? So if you know the maximum value, it would be PAB upon L. That means it would be equal to P, that is 1 into 3 into 6 upon 9. That means equal to 2 kilonewton. Fine. Now using triangular property, what we will say that 2 upon 6 will be equal to h upon 1.33. Okay, so if you will use that, you will get it to be 2.66 divided by 6, you will get it to be, so from this what you will get, this is your 2 kilonewton, okay, and your total length is 2. 2 kilonewton divided by 6 h upon 6 minus 1.33. Okay, 6 minus 1.33 into 2 divided by 6, it will give you h to be equal to 1.557. Similarly, if you take left side, your 2 upon 6 will be equal to, let's say I am writing it to be y upon, that side will be 3 minus 0.67, and if you try to find out y, you will get it to be, let me try it again, you will get it to be 1.553 553. 3 minus 0.67, okay, into, what is the maximum value, 2 divided by, this should be 3, yeah, 1.553. Okay, now we got the values of these ordinates. One is 1.557 and another we have calculated it to be 1.553. Fine. Now you know the value of ordinates. Now using trapezium rule, calculate the area that is coming under this section. Let me mark that area. So, okay, so this is your area. Okay, so this area you are expected to calculate this. Fine. So now area that will be covering this green region, that will determine the maximum bending moment area. Fine. So let's solve that. So your maximum bending moment, at C, it will be equal to 1 by 2 into sum of parallel sides, that is 2 plus 1.553, and what will the distance between the two? It is 0.67 into 0.67 plus, again we have another thing, that is one half sum of parallel sides, that is 2 plus 1.557, and what will be the distance between them? It is 1.33. Fine. Okay, this whole thing we have to multiply with load intensity. So here the load intensity is 30 kilonewton, multiply by 30, and it will give you the value as 106.67 kilonewton meter. Okay, so the area which is coming under the two ordinates in which we have divided the load ratios, that will give you the maximum bending moment at that particular region. Fine. So now let's move to another question. So your question 5 says that now the intensity of load of 45 kilonewton with span 2 meter is moving from left to right of beam AB as shown in question 3. Now you have to determine the absolute shear force. Earlier in the same question, using 30 kilonewton per meter load, we have determined maximum bending moment. Now you are expected to calculate maximum shear force. So for shear force, we have already seen in the I think third question, So if you have to determine the shear force, how you will make? We will divide it into such a manner based upon the ratios of length. Okay, so let's draw the shear force diagram for this beam. Okay, so how it will look like? As we already seen that the shear force is determined based upon the ratios of the length we have seen. Fine. So that means this value is 1 by 3, and this value we have calculated to be 2.2 by 3. This is plus, this is minus. Now, how we will get to obtain the maximum value of shear force? Okay, so what we will do, we will first keep the whole section of the shear of this loading intensity. I will draw the loading intensity also. So this, suppose this is your loading intensity of 45 kilonewton per meter, and first I will keep this to be on the right hand side of the beam, that means in this region, and then I will keep that to be on the left side of the region of the negative, because I am not worried about the sign. I am very worried about the absolute value that I will be going to obtain. Okay, so keeping, so for the case one, if I am keeping that case one load between C and B. Okay, so in this case, again we have to use, let me draw with the dotted line. So again we have to use principle of similar triangles. So what you will get? So 2 by 3, I will write like here, 2 by 3, what is the total length? 6 is equal to x upon, what is the distance? This distance is 2 meter. 2. Okay, so what you will get? You will get h to be equal to 4 upon 18, and that will be coming out to be, oh, I think it would be 4 upon, again I have done the wrong thing, it is 4, and then it will come out as 8 upon 18, that means 4 upon 9. Fine. So this ordinate is 4 upon 9. So we will find the area that will be coming under this section. So your shear force will become equal to 1 by 2 into sum of parallel sides, that is 2 by 3 plus 4 by 9 into 2, and what is the loading value? It is 45 kilonewton. So in this case, if you see, you will get the value to be 50 kilonewton. Now let's say case 2, when load is kept between A and C. So in that case, your 1 by 3 divided by 3 will become equal to x upon 1. That means your x will be equal to 1 upon 9. Okay, so that means your this ordinate for 2 meter length, for 2 meter length, this will be 1 by 9. Fine. So again, if we take the shear force, how we will determine? We will find the area coming in this section, that is 2 by 3, sorry, 1 by 3 plus 1 by 9, altitude is 2 and loading is 45 kilonewton. So in this case, what you will get? You will get the value to be 20 kilonewton. So your maximum shear force is occurring in case 1 and it is equal to 50 kilonewton. Fine? Okay, so let's solve another question. So in the next question, you have to draw the correct ILD, that is influence line diagram, of bending moment at point C, which is kept at a distance of 4 meter from support A. Okay, so for this, what you will do? So for bending moment, so if unit moment is applied at point E, okay, so that means you are providing a unit load at point E, okay. Now due to this unit load, you have to draw the bending moment diagram. Fine, so let's draw that. So we have to only draw the qualitative bending moment diagram due to this unit load, not calculate the values for that. Fine, let me arrange the lines as per the dimensions given. Yeah, now I think it's okay. So let's start drawing the ILD. So that means you're you're observing this point to be having the 1 kilonewton meter, and this point will be 0 because it is a hinge support and no movement will come here. It will be like this. Now again at point B, your bending moment will be 0. Okay, so it will be like this, and this can't stop like this abruptly. That means it will extend in the overhanging portion of the beam also. If I extend this line, it will be like this. Okay, so in this question, you are not expected to calculate the exact values of bending moment diagram. You have to just qualitatively draw how the bending moment diagram of this beam looks like. Fine, so I can write this to be, this part to be positive, this to be negative. Fine, and if I talk about supports, this is your support C, A, E, B and D. Okay, fine, let's move to another question. So your next question tells you draw the ILD for the shear force at point C. Now earlier we have drawn the bending moment diagram. Now we have to draw the shear force diagram at point C. So to draw the shear force diagram, what we will do? We will apply a unit shear at point E. Okay. So if you are applying unit shear, it will be like this. Fine. Now due to this, how you will draw the shear force diagram? Okay. As we have already seen, for the shear force, it is based upon the deflection profile of the beam. So if I say due to this unit load, it is applied at the 2 points of the beam, how the deflection profile will look like. So first draw that. So the if I am taking only this point load on the left hand side of the section, your deflection profile in the beam will look like this. I think for the convention I should write the in the opposite sense. Okay, so if I should write this to be downwards and this to be upwards. Okay, so if this is down, how your deflection profile will look like? Due to this downward shear force, it will be like this, and it will be like this. And in this case, since it is upwards, so again it will be like this and this. Fine. So this is your deflected profile of the beam due to unit shear at point A, at point C. So this is your deflected shape due to unit load. Okay, so now if we try to draw the shear force diagram, how it will look like. So it will be same as what we have experienced for the deflection profile. That is what we have seen in the first derivation. Again, it will go up here 1 kilonewton. Okay, so this is how your shear force diagram will look like. So your shear force diagram will be same as your deflection profile of the beam. Fine. So in this question, you are not expected to calculate the values. Just have to draw the qualitative shear force diagram. Bending moment diagram you have already drawn in the previous question. Similarly, you have drawn the shear force diagram. So whenever you are expecting to calculate shear force at one particular point, provide a unit shear at that particular point, then see what kind of deflection profile you will observe in that particular beam, and based upon that you will get the profile of the shear force diagram of the ILD at that particular point, that is C, that is E. Similarly, for the bending moment, as we have done in the previous question, you have to apply a unit moment in both the direction at that particular point where you are expected to calculate the bending moment diagram. Then you will draw the bending moment profile and see how it will look like. Fine. Now let's move to another question. In the next question, it is telling you if a point load, that is a concentrated load of 15 kilonewton, moves over the following beam, find the maximum reaction force at support B. So if you are expected to calculate maximum reaction force at support B, so as per Muller Breslau Principle, what you will do? You will provide a unit displacement to the support B. Now, whatever deflection profile you will observe, based upon that, you will get to know the maximum reaction force at support B. So, let me write in words, then it will be easy for you to understand that. So, to find influence line diagram for reaction force at support B, what you will do? You have to remove support B and apply an upward unit load then find the deflected shape. Fine. This is what Muller Breslau principle tells you, or you can say Betty's law that we have already seen. So, if I draw this diagram, how it will look like? Let me draw the lines as I have already written. So I will make sure the lines to be almost in the same range where the diagram is. Okay, is it fine? So let's continue further. So if we provide a unit displacement to support B, so let's say this is your unit displacement for support B. Okay, so now in this case your deflection at this point will be 0. Okay, so if this is 0, how it will look like this, and it will continue till this point, till point C, because there is internal hinge there. Now again you can see that shear force, or yeah, the shear force at point A will also be 0. Then it will continue like this. Fine. So this is how your profile will look like. So this is your unit load. So let me write, this is your unit load. So if this value is 1, okay, so what will be this value that we have to calculate at point C? So this is A, C, D, B. Now if we try to calculate this value, so how it will look like? So suppose this is X. So how you will determine the value of X? So your X upon 2 will be equal to 1 upon 5. This will give you X to be equal to 2 by 5 equal to 0.4. Fine. That means you will get the maximum value only when you will kept the load at point B, because that is the maximum ordinate you are observing. So let me write that maximum reaction force at support B will be when the 15 kilonewton load is placed at point B. So the value of shear force at B will be equal to 15 into 1 equal to 15 kilonewton. Fine. Because we have calculated both the ordinates, the second ordinate at C, it is coming out to be zero point 0.4. So that means only if you keep the unit load at point B, then only you will get the maximum shear force. So if we try to calculate the maximum shear force value, we will get it as 15 kilonewton. Fine. Now your next question is, now instead of having a single unit load, if you are having a two load system of 20 kilonewton and 25 kilonewton, which is separated by a 2 meter distance and it is moving from left to right on the beam. Now, if you are expected to calculate the shear force, maximum shear force in the beam, then how you will do that? So, maximum shear force, if you are expected to calculate, since there is no loading, so maximum shear force will only come in the two cases. First case is when the 20 kilonewton load is kept at reaction A, or second case is when 25 kilonewton load is kept at reaction B. So we'll take both the cases, and out of both the cases, which one will give you maximum shear force will become your absolute maximum shear force. Okay, so for this question, let me take for case 1, I will draw the shear force diagram as we have previously drawn. So again, in this case, if I will draw the shear force diagram, how it will look like. So if I am drawing the shear force diagram for the support A, what I will do, I will provide a unit displacement at point A. Fine. So if I provide unit displacement, that means this will be a unit. Fine. Now that means this load assembly will now be kept over this beam. Okay, if I paste it there like this, let me small this. Okay, now if I am placing this load assembly here, that means we are expecting the shear force at 2 points. This, since we already know this value to be 1, and what will be this value? This value we will calculate as, let me solve here only. So I will write this to be x to be equal to 1 upon, so x, if I will solve, that means 1 upon 20 will be equal to x upon 18. This will give you x to be 18 upon 20, that means 0.9. Okay, so your this value is 0.9. So this is your ILD for reaction A. If I try to determine the shear force in this case, so shear force for reaction A, it will be equal to 20 into 1 plus 25 into 0.9. So what you will get the value? You will get the value as 42.5 kilo Newton. Now, again what we will do, we will take this and we will put the load in another load assembly. So let me draw again two lines. Let's say the distance between these two lines is 20 meter, and I am providing unit displacement at load at reaction RB. Okay, if you are providing unit displacement at reaction RB, so this is how your shear force diagram looks like. Fine. Now in this case, if you will put the loading configuration again over the beam, how it will look like? I am again putting this loading configuration here. Okay. Now here we know that this distance is 1. And what will be this distance? We will again calculate it. We will again calculate this distance. Let me draw this line. Let's say this is y. I will write it to be y upon total distance is 18 equal to 1 upon 20. This will give you y to be equal to 0.9. So now this value is 0.9. So this is your case 2. I have to mention here also. So for case 2, so now your shear force for reaction B will become 20 into zero point 0.9 plus 25 into 1, and that will give you a value equal to 43 kilonewton. So your maximum shear force is coming out when your load of 25 kilonewton is kept at point B. Okay, so your absolute maximum shear force will be equal to 43 kilo Newton. Fine. Now let's solve one more problem. So in this case, now instead of finding the maximum shear force, you have to determine absolute maximum bending moment. So, so to get absolute bending moment, we have to divide the load in such a way that the center of the beam will be equidistant from the load CG and the nearest maximum load. Okay, so what I am trying to explain to you, so we will first determine the CG of this loading, or you can say loading arrangement. Okay, so CG of loading arrangement, how it will look like, means at how much distance it will come. Let me mark it to be at a distance of x. Fine. So here x upon 2 meter, or you can say your total load, how you will define the CG, your x will be equal to, since I am taking from this point, that means 20 into 0 plus 25 into 2 divided by 20 plus 25. Okay, what it will look like? It will be 50 upon 45 equal to 1.11 meter. So that means your x, that means CG of the loading arrangement is at a distance of 1.11 meter from load 20 kilonewton. Okay, so let me write here that to get maximum bending moment the load is placed in such a way that center of the beam, because it is a simply supported beam, so center of the beam will be equidistant from load CG and nearest maximum load. Okay, so out of these two, maximum load is 25 kilonewton. Okay, so that means if one distance is 1.11, so your other distance will be, let me copy this diagram and we will see in the next page. Copy. So if your x is, let me write it as y. So if your x is 1.11 meter, then your y will become 2 minus 1.11 equal to 0.89. And as per the definition, you have to keep the load in such a manner that it will be as a equidistant from point A. Let me draw and then I will explain you. Then it will be easy to explain. So suppose this is our beam, simply supported beam. Okay. So in this, at the center, so suppose this is my center. So if this is my center, the load should be kept in such a way that the 25 kilonewton will be as a equidistant from the distance of the CG. That means I have to keep 25 kilonewton here and 20 kilonewton here. Okay, so this is 25 kilonewton and this will be 20 kilonewton, and this distance C is as a most important thing, that this distance will be 0.89 divided by 2 to be equal to 0.445. Fine. And your this distance then now will become 0.445, 0.11 plus 0.445, because half now went to this side and it will become 1.555. Fine. So this is your point A, this is your point B, and let's say your center is at point C. Okay, so this is how you have to distribute the beam. So maximum bending moment will come under the net maximum load. Okay, so let's find out. So if I try to determine the moment, so my RB into 20 will be equal to 20 into what is this distance? This distance will be, total is, center is 10, 10 minus, we have already calculated that distance to be 1.555, plus next is 25, 25 into 10 plus 0.445. Solve this, you will get the value of RB Okay, and this RB is coming out to be 21.50125 kilo Newton. So since maximum bending moment will come under 25 kilonewton load, which is maximum of both of them. Okay, so your moment, your maximum bending moment, it will be equal to RB into that distance, and that distance is 10 minus 0.445. Okay, that will be the distance at 20 under 25 kilonewton node now. So that value will come out as 21.50125 into 10 minus 0.445, and that will be equal to 205.44 kilonewton meter. So fine. So if you are expected to calculate the maximum bending moment, like we have done for the shear force, because in the shear force, two loads are there, and you know that maximum shear force will come at any of the points because of the deflection profile of the beam. So we have calculated the shear force in both the cases. Whereas in bending moment, what we did in this, we have to first divide the loading arrangement based upon the CG of the loading arrangement. Then based upon the maximum, we can say maximum load, you have to keep the maximum load as a at a at a equidistant from the center of the beam. So that's why your point 8, what is that, 0.89 will become 0.445. So that's why you have kept your 0.89 load as at a distance of 0.445 from the center, and your next load, that is 20 kilonewton load, will be kept as at a distance of 1.555 from the center of the beam. So now you already know that the maximum bending moment will come at the point where the maximum load is occurring, that is 25 kilonewton load. And if you have to determine the maximum bending moment at that particular point, we have determined the reaction force B, and from that reaction force B multiplied by the distance between the 25 kilonewton load and the reaction B, we are able to calculate the bending moment under the 25 kilonewton load. Okay, so this is what we have covered in this current week. We started with the problems related to defining how the influence line diagram under unit load are defined, in which we have seen first, if a unit load moves at two different points at the beam, then how the shear force diagram looks like. Then we have solved some problems related to concentrated load as well as the uniformly distributed load. If they are kept at different locations, then how the ILD diagram looks like. Or if you are required to calculate the maximum shear force and the bending moment due to your moving loads, so at how much distance or at what position you have to keep the loads, and what value of maximum shear force and bending moment you are expected to get from them, you have calculated. And finally we have just concluded with determining the maximum concentrated load, maximum shear force and bending moment for a loading arrangement diagram in which two concentrated load are kept at certain distance. So this week we have covered all the topics related to influence line diagram, wherein a moving load is making its way from left to right along the beam, and based upon that we have calculated different reaction forces, then shear force, bending moment using Muller Breslau principle. And from the next week, we will see the problems related to statically indeterminate structures. I hope this video will be useful to you for solving all the problems related to influence line diagram. Okay, so let's wrap up this session. We will meet next week on Saturday. So till then, enjoy your weekend, solve your assignment, and try to complete before the due date. So thank you everyone. Have a nice day.